Alright, so we're talking about the Simpsons. No, we're not. We're talking about Simpsons Rule, and it's actually a handy method of numerical integration. Okay, and what I want to do is link back to what you should have learned already, certainly if you're watching this video. Some areas under a curve, approximation type techniques, which of course link to integration. Okay, and they link to calculus, but they also link to numerical integration too, which is an approximation technique. Perhaps you've been through the approximation of the area under a curve over a certain interval. You might have seen using rectangular strips as a method. Okay, so if the interval is between 2 and 5, we can use left-hand strips where the point of contact is on the left side of each rectangular strip, and the intersection between the top left corner and the actual curve of the function dictates what the height used will be. And in a falling curve like this, obviously it's dependent on how many strips too, okay, and various other things, the nature of the function, all those sort of things. But in a case like this, it will overread the area under that curve over that interval. So that's left-hand strips. The opposite situation for the same curve will underread slightly. You can see the gaps there, and there'll be an error for the same sort of curve. And this left-hand strips method to right-hand strips method, I should say, will have a smaller area estimate than the left-hand strips. Okay, but they both, you can see they both got error because this has got parts protruding out and this has voids there. So what you might have learned after that is an average of the left and the right hand method. And by the way, you can get the center method as well too, but it has issues as well. But if you want an average of those two, you have what's called the trapezoidal rule or the trapezium rule. So you may have learned that trapezium rule, instead of rectangular strips, they're trapezoidal strips, which is pretty much a rectangle until you get to the top, and the top has a trapezoidal profile there. So what I mean is that they're basically, for a falling function, they will be trapezoidal, unlike the earlier rectangles. Oh, that's not a rectangle. Okay, so you have a trapezoidal approximation there. And again, it can be good. It is limited by the number of strips and the nature of the function there too. And you may have learned a form of the trapezoidal rule, the formula for approximate area. You may have learned that there, or an equivalent that uses different symbols. Okay, and we divide things up into equal length strips, and we've got ordinate points and so on and so on. We've got end values and middle values and so on. But we can actually come up with something, yes, it's more sophisticated, but actually it is somewhat better. And under some circumstances, it is exact. I rule indeed. We have Simpsons Rule, where we've got set up like that, not unlike the setups we saw a bit earlier, and we have parabolic tops. Okay, so instead of rectangle, trapezium, which seems a bit more sophisticated, we now can model the top with parabolas. Okay, so an indicative diagram might be this one here, where there is some area in the trapezoidal rule, but less to none in the Simpsons rule. There is definitely a proof for this, and how it works and why the formula is what it is, but that's outside the scope of this video. That would take up a bit of time. But certainly there is one that you'd probably be able to understand too, fairly thoroughly, given some extra time. Now, why do we need this? Well, this method would be used, this type of numerical integration method would be used if we've got some data that was measured out and we don't have a discernible continuous sort of function or functions to model the area that we need. Okay, so it's where we can't use calculus. There's not a suitable function or not a known function. It doesn't follow any function. So that's where we would use this. And in some cases, Simpsons Rule does an excellent job. In most cases, provided we've got, you know, sufficient strips and so on, we come up with a good approximation most of the time with it. Example might be this situation here when you've got a road to be built cutting through a hillside, and we've got you know, an area. So when we look at the cutting, the profile, and if we need to know the area of that profile, perhaps for the roadworks crew when they're trying to stabilize the bank, we can work that out if we have sufficient measurements. For example, for an 80-meter cutting, we've got heights taken every 10 meters, and that would accrue some data, and we could use that. And sometimes that can be applied further into volume. So that's just an example. So not unlike the trapezoidal rule, we have a certain setup with some certain symbols meaning particular things. So if we have some function or not between the interval a and b, we can approximate a given function, or we can use this process when there is no function and we have sufficient data taken at regular intervals or regular subintervals. Okay, but for interval AB, we can approximate the area as follows. Now it's split into n strips. Okay, the strips must be equal width, which is denoted by W, and all the intervals are split up by these, which relate to the ordinate lines that go upwards. So the first line, and it's also the same as that lower end of the numerical integral, is called A0. Then the next one is called A1. So please note that the first one is not called A1, it's called A0, and it's the same as that A there. All right, and it keeps going, and depending on how many strips you are, eventually you get to the last one, which of course, if there's n strips, the last one would be A sub n, and that would be the same as B. Now, here's an important stipulation with Simpsons rule. You need to have an even number of strips, so n is always even. Okay, I've seen some people try to use Simpsons rule and they've got n equals 5. That's not valid. Okay, and the proof can show that. Okay, so here's one form of it. So here's an expanded form. Notice how on the first line it says approximately equal to, and then it says equals there. Now that means the area, if it's the approximating area of a given function, we write approximately equal to. Okay, sometimes if it's degree 3 or less, in fact, whenever it is a polynomial of degree 3 or less, Simpsons rule is exact. That's pretty amazing, isn't it? And that can be proven as well. All others will be approximations, and that's why we write approximately there. Now this here is the expanded form. So it's 1/3 times the strip width times f of A0. So that goes back to these symbols back here. So f of A0 is the first position of where the first ordinate line comes up from, and we're just subbing whatever value that is into the function. There's your function notation. So sub A0 in, and again this can be found by proof, but if we do 4 times f of A1 plus 2 times f of A2, 4 times f of A3, see how it alternates between 2 and 4? And there are reasons for that which go beyond the scope of this video, but it is an interesting activity. Up to 1 of f of a to the n, we get the area approximated. Now, that's expanded form is a bit especially when there's a lot of strips, that is a bit cumbersome. So what we do is we use some intelligent use of symbols, and basically it's going to get a better color because there's too much green going on. We come up with, that's a good working formula, provided you know what capital X, capital E, and capital O mean. Now, a little bit like some applications of the trapezoidal rule, X is the extremes or the end values. I think of X, extreme, all right, the X sound. So it's the sum of the two end values. Did you see that there? So there's only one lot of that, okay? So it's f of a naught plus f of a sub n, all right? Then we go 2 times e. Now e is all of the even ordinates, okay? Denoted by that subs there. So 2, 4, if there's 6, 8, 10, all right? But don't include the n ones because they're included up there, all right? And O is for the odd ones, all right? F of A, 1, 3, 5, okay? Now, remember, it starts at A naught. It doesn't start at A1. Be careful. All right, and again, don't include the n's. Well, you won't if it's even anyway. That is the form you'll use in bread and butter style questions. Okay, other slightly different notation, you might see it like this. This is sort of a middle ground between expanded and compressed notation. So that was expanded up there, and that was more compressed there. This is sort of a middle ground. It's the same thing. I scrolled too far. So you can see that it's the extremes, 4 times the odds, and 2 times the evens. Okay, it's the same thing. All right. You could derive the rule by using your usual calculus methods and going through a derivation, but it's beyond the scope of this. Let's finish by doing a fairly mid-level sort of question. So we've talked about polynomials, but you can certainly use this on other functions like this trigonometric function which has a radical there too. Okay, so use Simpsons rule of 4 strips. So some questions tell you how many strips to use. The more the better, okay, unless it's a squared or a cubic polynomial, and it doesn't matter, you just do as minimal strips as possible and you'll get the exact answer. But with other ones, you're better off going for more strips if you want more precision, albeit that requires more work, and that's the disadvantage of this method. It can be inefficient perhaps if there's better ways of doing it, because you don't always get the exact answer, and it has a lot of calculation involved in it. Okay, so it's got pros and cons. All right, so what I would suggest that even though this is a by hand question, if you're allowed to use a graphics calculator to, especially for something like this, it's not easy to graph without technology, I'd get a bit of a drawing happening and then I'd sketch the drawing. So using some graphing calculator, you could use that also to do an integration in the interval too. So we know that the actual answer is in the vicinity of 1.12, and we know the shape of it. So let's work that question through now, and we basically need to know where the ordinate lines are. So it's important to do by hand sketch as well. Okay, and it sort of comes up like that, and if I put, let's say, what do you got? 1, 2, 3, 4. So I'll put 1 there, 2 there. Okay, so we're going between 0 and pi on 2. Pi on 2 is about 1.57. All right, and 1.5 is there, so that's where my pi on 2 is going to be. Okay, now the strip width. We have 4 strips. It's said in the question. All right, if we go back, it says 4 strips, and they've got to be equal width. So we've got to work out the strip width, which is W. So we've got, what's the width of our interval? It's from 0 to pi on 2. So it's pi on 2 divided by 4, which is pi on 8. So each strip is going to be pi on 8 wide. Okay, now pi on 8 is roughly 0.4 units. Okay, so just to get an idea of where to put these lines, so 0.5 would be there, so 0.4. So there's pi on 8 there. We need another 2 pi on 8 or pi on 4, so it'll be about there. And so 2 pi on 8, in other words pi on 4, and 3 pi on 8 would be about 1.2 and a bit. Alright, so you can see we've got our strips coming along there. Okay, so now we're ready to identify the things that need to go into the formula, such as X, E, and O. So writing the formula down, the area, or in other words, the approximation of from B to A of f of x dx, approximately equal to, you're going to use the working version of that formula, 1/3 w, or w on 3 you could write, upper x, 2 upper e, and 4 upper o. At this point, you could break this into smaller parts, and we need to look at what E, X, E, and O look like. Okay, so we've basically, X is the ends, so X will be f of naught. Okay, because A of naught in this case is 0. Alright, and A of 1 is pi on 8. A of 2 is pi on 4. A of, that's a 4. A on 3, 3 pi on 8. That should have been an 8 there before. That was a bit of a goof. And 4. Alright, so there's actually 5 numbers going on there because there's 5 boundaries for 4 strips, right? Of course there is. And we've got, x equals f of naught plus, that should be a plus f of 2. Alright, that end one there. So put 2 inside the function, which if you calculate that, put 0 into the, put 0 there, it's 0. We put the value for f of 2, put 2 into the function. Alright, you're putting it into the function that we started with. Alright, so an example would be, you're going to use your calculator for all this, but sine of root 2. Sorry, that was sine of root pi on 4. I grabbed the wrong number there. Okay, and you would get about 0.7 0.775. Okay, so you got to calculate all these. That's just an example, but for that end ordinate, it should have been pi on 2 under the radical sign there. So that's about 0.950 to 3 decimal places there. So in other words, that's what f of 2 was, the other extreme. Okay, so you'll see that number go in now. So 950, 950. Okay, and we keep going. I'll go a bit quicker now. So we want to get E, but really we want to get 2E. So I might as well put the times 2 there, because that way it'll go straight into the formula. And we got, there's only one even ordinate, okay? And it's the A of 2. All the others are either ends or they're odd. Okay, so it's pi on 4. So f of pi on 4, which I worked out just a moment ago, you might recall. Okay, f of pi on 4 and that'll be, you don't necessarily need to show all this working here, but just for the sake of understanding, being the first video, I'm spending a little bit longer there showing that working. Alright, and then 4 times the odds, 4 times f of the odd ordinate positions, and you can scroll back and see that again if you need to, where those numbers came from. And we have 4 times 0.586, that comes out as 0.884. Alright, and then area, or it depends if it's asking you for the approximate area or the value of the integral. Alright, so just a little thing there. If it's asking you for the integral, you write that. So perhaps I should have wrote that for this one, or if it's an area, you say area. Okay. So I'll probably do it properly then. So we're approximating a given function, so we really are writing this down. Okay, and so we've got w on 3, alright, which is pi on 8 on 3. 8 3s are 24, so it's pi on 24 outside of x, x is 0.950, sorry, and we have our 2e, which is 2 times 0.775, and lastly 4 times o, which is 4 times that, and we've just about finished now. 0.884. Okay, so